These are examples for section 14.5, volume of pyramids and cones. Example 1, architecture. The entrance to the Louvre Museum in Paris, France, is a square pyramid with the height of 21.64 meters. What is the approximate volume of the Louvre pyramid? Okay, so we're looking for the volume of this pyramid. Maybe they want to know how much AC can fill up the inside of the pyramid museum, something like that. And here's a model of the Louvre below the photograph of it, and they said it was a square base, so this is one side, so all four sides are congruent, and they tell us that the height is 21.64 meters. They didn't give us the height dimension on the diagram, so we're going to take a straight edge and draw the height. Remember, the height of any solid is perpendicular to its base face, the polyhedron. And so here's the height, which is 21.64 meters. Now, starting with this lesson, I'm going to go ahead and plug in all values into the original formula as we go forward. So the volume of a pyramid is V equal 1/3 the area of the base face times the height of the pyramid. And here the base, or big B, is going to be S squared because it's a square. So I'm going to go ahead and plug in over here, substitute. So we have 1/3 times big B, which is S squared, times the height of the pyramid. And so the height of the pyramid, as we just got through saying, is 21.64 meters. And big B is S squared, so S is what they gave us, 35.4 meters. So we have everything we need. We have V equals 1/3 times S, which is 35.4, times the height of the pyramid, which is 21.64. The 3 doesn't necessarily go into either one of these numbers evenly, so we leave 1/3 for right now. 35.4 times, that's squared. Square that. 35.4 squared then is 1,253.16 times the height, 21.64. So the volume is 1/3 of, and then we can multiply these two together, we get 27,118.382. And so at this point, this is the same as saying 27,118.382 thirds, because as we said in the notes, multiplying by 1/3 is exactly the same as dividing by 3, the whole number 3. So that would be an exact answer, but they asked for an approximation. So the volume, when you divide that in your calculator, dividing by 3, you get about 9,039.5 cubic meters, rounding to the nearest tenth of a cubic meter. So there's practically way over 9,000 cubic meters of space inside the Louvre Museum pyramid. Example 2. What is the volume in cubic feet of a square pyramid with base edges of 40 feet and slant height of 25 feet? So here we have another square prism. All four sides of the square base are 40 feet. And we have the height drawn here, which is perpendicular. And from here to here would, of course, be half the base length. So this is 20 feet. So bringing this triangle out with the slant height of 25, hypotenuse would be 25, this would be your 20 feet, and this is the height. Looks like a rather short pyramid. So for the volume, we have V equals 1/3 times the area of the base face times the height of the pyramid. And so, substituting in for what big B is the area of a square, so that's 1/3 times S squared times the height of the pyramid. So finding our dimensions, first of all, the any side of one of the bases is 40 feet. And then we need our height. We're going to have to find our height using Pythagorean theorem. Hypotenuse 25 squared equals height, or h squared, plus half the base length, 20 squared. 25 squared is 625 equals h squared plus 20 squared is 400. Subtracting 400 from both sides, h squared will give us 225. Take the square root of both sides to get h by itself. This happens to be a perfect square, and that's 15. So our height is 15 feet exactly. Now we have everything we need. The volume is 1/3 times S, which is 40 squared, times the height of the pyramid we found was 15. All these numbers are being multiplied together. Of course, we need to square the 40, but we can first notice that 15 and 3 are divisible by 3. Since they're all factors, we can go ahead and divide those out. 3 goes into 3 once, 3 goes into 15 5 times. So now we have 40 squared, which is 1600, times 5. 3 is no longer there. So the volume of this pyramid is exactly 8,000 cubic feet. Example 3. What is the area of the base of a pyramid whose volume is 900 cubic centimeters and whose slant height is 6 times the square root of 5 centimeters high and an apothem of 6 centimeters? In this problem, of course, we're dealing with volume, but we're not finding the volume. The volume is already given. The volume is 900 cubic centimeters of this pyramid, what's inside. And they're asking us for the base, the area of the base pyramid, which is big B. And sometimes they'll ask you for, let's say they asked us for the apothem, or they asked us for the side length of the base. Well, then at that point we need to go ahead and determine that big B would be 1/2 AP, the area, so that we could find those. But in this problem, it's relatively simple because they're just asking us for the area of the base, which means our answer is going to be in square units. This is what we're looking for right here. But so we still start out with the volume formula, which is V equal 1/3 big B H times the height of the pyramid here. And so we can find big B directly. We don't have to, we don't need to find S or any of the parts of B. And so we have our volume, so we have that. And big B is what we're looking for. And then, of course, the height, the slant height, they tell us, is 6 times the square root of 5. So we need to find our height. Here's the height of the pyramid, the actual height perpendicular to the base face. Here's our slant height they give us right here. So this is 6 times the square root of 5 centimeters. And so if we bring that triangle out, that right triangle, this would be our slant height, our hypotenuse. This is L. And we have the height, which we're looking for. And then they told us up here in the problem, the apothem, this apothem right here, is 6 centimeters. So this would be 6. So we have this right triangle, and we can use Pythagorean theorem. Since we have 2 of the 3 sides of that right triangle. The hypotenuse, 6 times the square root of 5 squared, equals h squared, the height squared, plus the other leg of this right triangle, 6 squared. Be careful when you square a number with a rational and irrational part. Both parts get squared. So this is 6 squared times the square root of 5 squared equals h squared plus 6 squared is 36. 6 squared is 36 times the square root of 5 squared is the square root of 25, which is, again, just 5, equals h squared plus 36. 36 times 5 is 180, equals h squared plus 36. Solving for h squared and then h, subtract 36 from both sides, and 180 minus 36 gives us 144. Taking the square root of both sides to get h by itself, we get h is 12. So we have our height of our pyramid right here, which we need here. So we've got that now. So our volume again was 900. We substitute that in, equals 1/3 times big B, which is what we're looking for, the area of the base, times the height of the pyramid, which we found to be 12. 1/3 and 12 are divisible by 3, so 3 goes into 3 once, 3 goes into 12 4 times. So we get 900 equals 4b. Divide both sides by 4, of course. And big B, or the area of the base face, which this is a hexagon, is 225 square centimeters. Remember, this is the area of the base, square units. So the area of this base face here, this hexagon, and this pyramid is 225 square centimeters. Example 4. What is the volume of the oblique cone at the right? Give your answer in terms of pi and also round it to the nearest cubic foot. Even though we're given an oblique cone, for volume, we can find it the same way we would find the volume of a right cone. It doesn't really matter as long as we have the height or can find the height. And the height is always perpendicular to the base face, which of course is this circle. And so this is the height, 25 feet. Also, they give us the diameter's 30 feet, so we'll need the radius. So we're finding the volume. That's the volume of a cone is 1/3 times the area of the base face times the height of the cone. Big B, or the area of the base, of course, is a circle. So we use pi r squared. So this is 1/3 times pi r squared times the height of the cone. Defining all our variables, of course our height again was 25 feet, height of the cone. Our radius is the diameter divided by 2, or half the diameter, so that's 30 feet divided by 2, so the radius is 15 feet. Now we have what we need. The volume is 1/3 times pi times the radius, which is 15 squared, times the height, which is 25. Remember, we cannot divide out 3 and 15 because we need to square 15 first. You always square before you multiply or divide. Order of operations. So the volume is 1/3 times 15 squared is 225 pi times 25. Now 3 will go into 225 because it would have gone into 15, which is a factor of it. So 3 goes into 3 once, and 3 goes into 225 75 times. So now we have the volume is equal to 75 pi times 25. 3 is gone. 75 times 25 is 1,875 pi cubic feet. That's the volume, the exact volume of this cone, this oblique cone, and the approximate volume then is 1,875 times pi, which is about 5,890 cubic feet, rounded to the nearest cubic foot. Example 5. The covering on a TP rests on poles that come together like concurrent lines. If you recall what concurrent lines are from months ago. The resulting structure approximates a cone. It says this resulting structure approximates a cone. And so our cone here is not a perfect, necessarily right cone. I've drawn a kind of a skeleton of it here, and you'll notice it doesn't exactly go to the center of the circle. The height doesn't. But we're going to go ahead and assume that it's a right cone. You'll see the reason why in a moment. If the TP pictured is 12 feet high, so up from the ground up to here's 12 feet high, so that's the height, and the base diameter is 14 feet, all the way across the base, 14 feet. What is the approximate volume? So we're going to find the volume. And then also, how much animal hide was used to make the TP? That's not volume. How much animal hide implies area, surface area, but it only implies lateral surface area, where you assume that the animal hide may not be on the floor of the TP, so it's just the lateral area. So first we'll find volume, then we'll find lateral area. So starting with the volume of a cone is 1/3 times the area of the base, which is a circle this time, of course, this times height of the cone. And so finding that first, using our diagram here, the height of the cone is 12 feet. We also need the radius. The radius is the diameter, which they gave us is 14 divided by 2 gives us 7. So the radius is 7 feet. This is all we need for the volume. The volume is 1/3 times big B, which is pi r squared, times the height of the cone. So the volume is 1/3 times pi times the radius, which we found to be 7 squared, times the height of the cone, which is 12. I noticed that 3 and 12 are divisible by 3. 3 goes into 3 once. 3 goes into 12 4 times. Now we have 7 squared, or 49 pi, times 4. So the volume, the exact volume, is 49 pi times 4, which is 196 pi cubic feet. They asked for an approximation, so in your calculator, 196 times pi is about 615.8 cubic feet for the volume. And then the second part of our problem, we're going to find how much animal hide, which again implies lateral surface area. So the lateral area of a cone from the previous lesson is pi times the radius times the slant height. We already have the radius, of course, from above, but now we need the slant height. And this is the reason why we have to assume right cone, because it's almost a right cone, so we're going to go ahead and make it that way, because in an oblique cone we wouldn't be able to find the slant height here because there's so many different slant heights. So we're going to use this as our radius and assume it goes to the center. That means our right triangle here will have 7 for our radius, just like we indicated, and our height is 12, and we're going to use the Pythagorean theorem. So basically we're going to assume or act like this is a right triangle and the slant height is the hypotenuse. So this would be 7 and this would be 12. So by the Pythagorean theorem, we have the slant height, the hypotenuse squared, equals 7 squared plus 12 squared. So L squared is equal to 7 squared, or 49, plus 12 squared, or 144. So L squared is equal to 49 plus 144, which is 193. We want to solve for L. We take the square root of both sides, and so L is the square root of 193. And unfortunately, 193 doesn't have any perfect square factors, and it's not a perfect square itself. So we leave it like that for right now. There's our L. Substituting in, we have pi times the radius, 7, times the slant height, the square root of 193. If they had asked for an exact answer, we would have simply written this, 7 pi times the square root of 193 cubic feet, or excuse me, square feet. But they asked for the approximation. So with your calculator, put in 7 times second pi times the square root of 193. Get out of the square root, enter. You should get about 305.5 square feet of animal hide. So there's our second answer. That's how much animal hide covers it. Example 6. Find the volume of the hollowed out, non-shaded region of space to the nearest cubic millimeter. So we have a composite figure here. Looks a little bit like a traffic cone or something, but the shaded region, usually a lot of problems where we end up finding the area or volume, in this case of the shaded area, shaded region or space, but in this one they're asking for the hollowed out non-shaded region. So we're going to be looking for the volume of this space in here that of course goes all around that inner cone on the outside of it. So there must be some kind of hollowed out piece here that we're looking for. And you'll notice we have two cones. We've got an outer cone and an inner cone. So let's go ahead, and so that we don't make our formula a little too long, let's define what outer and inner are. Outer cone, suppose we could use O for outer, and for inner cone let's just use I for inner. So we'll use these as subscripts. And so the volume of this composition or composite solid here, how to find the volume of this space in between the two cones means we're going to take the larger cone volume, or the outer cone volume, V sub O, and then we're going to take the volume of the inner cone, because when we take the volume of the outer cone we find everything inside, every bit, even including the small cone. So we need to take out this inner cone, whatever's inside it, so that we can get what remains in between. So that means we're going to subtract the volume of the inner cone. So that's our very basic formula there. And so for volume formula for a cone, of course, is 1/3 big BH. So let's go ahead and put those in. That's 1/3 big B sub O, H sub O. Both of them are for indicate the outer cone, minus 1/3 big B sub I, height of the cone sub I. Now we can factor out the 1/3 so we don't have to keep writing it over and over. So 1/3 times big B, I'm just going to go ahead and use 1O now, big B H sub O minus big B H sub I. Now we can't factor out the B's or the H's because they all have different measurements. So let's go ahead and put in our detailed formulas. Both of these are cones, so their bases are circles. So pi r squared, of course, is our general base area formula. So we have 1/3 times big B is pi r squared H, and of course these are O sub O's here, minus big B, which is pi r squared, and then times the height of the cone. Both of these are the inner cones. Now let's define our variables. We have our outer and our inner cone. In our outer cone, we need the radius and the height, and these are subos. And in our inner cone, we also need our radius and our height, and these are subis. So, the only one you have to be careful of if you're not paying attention is the radius of the outer cone. So, in the radius in the outer cone, of course, we start at the center of the base circle, which is this big one, and we move out to the cone itself. Well, this indicates this is 4 millimeters, so we need this also. Well, how much that is? This whole diameter for the big cone is 16, so half of it would be the radius from here to here. And of course, that's 8. So the radius of the big cone is 8 millimeters. Then the height of the outer cone is from here all the way up, and that's of course 16. So 16 millimeters. In the inner cone, the radius starts from the center and goes out to that where the shading ends. And since this is 4 here, this has to be 4 here, so that the radius is 8 for the bigger one. So this is 4. So the radius of the inner cone is 4 millimeters. And the height of the smaller cone, of course, is 8 millimeters. Now that we have that straight and recorded, listed, we come back over here and start substituting in. We have 1/3 times pi times r sub o, which is 8 squared, times h sub o, which is 16, minus pi times r sub I, which is 4, and don't forget to square it, times the height, h sub I, is 8. That's our plugged in or substituted in step. Now we have 1/3 working inside the parentheses. There's 2 terms here separated by a subtraction sign. So 8 squared is 64 times pi times 16, minus 4 squared is 16 pi times 8. Simplifying further, we get 1/3 times 64 times 16 is 1024 pi, minus 16 times 8 is 128 pi. These are both pi terms, so we can subtract those. We have 1/3 times 1024 pi minus 128 pi is 896 pi. Now, 896 is not divisible by 3, and the reason why I know that so quickly is because I happen to know the divisibility rule for 3. Add the digits. If the sum of adding the digits, that sum is not divisible by 3, then this number is not divisible by 3, like this. 8 plus 9 is 17, and then you add 6 to 17, 23, and 3 won't go into 23, so it will not go into 896. So we are left with 896 thirds pi, which is the volume of our composite. Now, they did ask for the approximation. This would be our exact answer in cubic millimeters, but the volume approximated 896 divided by 3, enter, and then times pi, or you can do 896 times pi and then divide by 3. But be careful not to put the pi down here accidentally in your calculator. We get about 938 cubic millimeters for the volume of this space in between the 2 cones.